In section 3.1, we get our introduction to the types of lines and the types of angles we're going to be looking at throughout this chapter. And the first types are parallel lines. So two lines are parallel lines if they are coplanar and do not intersect. So we say coplanar, meaning they're on the same plane, and they never intersect. So far we've talked about how lines can intersect at a point, but we haven't quite addressed that if they don't intersect. So this is where we'll define it as if they do not intersect and they are on the same plane, we will call them parallel. We typically put little arrow markings there to signify parallel. If I had L and M, I could say L is parallel to M. Now, that applies to lines. We can also have the same idea with planes. Two planes that do not intersect are parallel planes. So I have this box over here on the right, which we'll get to the examples in a minute. But if we thought of this box as like a classroom or a room you're in, the parallel planes could be the top, the ceiling that you have, and the floor. They're both plane surfaces, and let's draw these in here. They're both plane surfaces that do not intersect. Floor and the ceiling would be one, left wall, right wall would be the other, front and back could also be another. So those are parallel planes. To go back to parallel lines, I have AD and EH here. They're on the same plane, that front wall, but they will never intersect. The other type we have is lines that do not intersect and are not coplanar are called skew lines. So these don't intersect and are coplanar. These don't intersect and are not coplanar. So we can't represent them on the same plane. They will not intersect. So if I looked at this box here, let's look at CD. Here's one of my lines. I need a line that does not intersect with it, so it doesn't hit at C or D, but it's not also on the same plane. So if I looked at AE and CD, they're not on the same plane, they don't have the same plane in common, they'll never intersect. So that's the difference really between skew and parallel. So let's take this idea and start to label some things. So I have my diagram here. I'm looking for a line parallel to AB that contains point D. So here's point D here. So parallel to AB has to be on the same plane, but goes through point D. So we're looking for a line that's on that same plane. It includes D and parallel to AB. We can think of that ceiling as that plane, and the ceiling also has line CD. So that one would be parallel, so we'd say line CD. The next one, I'm looking for a line perpendicular to AB that contains D. Now, I didn't quite mention this, but we're going to assume all intersections in this diagram are right angles. So I'm looking for a line that intersects with AB and is on the same plane. If we look here, we get a right angle at point A, so I'm going to call that AD. Now I'm looking for a line skew to AB that contains D. So it's not on the same plane, but so far we've talked about this line was parallel, this one was perpendicular. If I looked at DH, that would be a line not on the same plane. It does not intersect to AB, so DH would be my skew line. Last, we need to name a plane that is parallel to plane ABE and contains D. Plane ABE is this wall we have over here. A parallel plane to that would be the right wall. And we can name that plane really any three letters of D, C, G, and H. So how about we just say CDG? But again, any of three of those four letters, name them together, and that would be the plane. Now let's carry on with parallel, and then we actually add perpendicular. Now we have an actual postulate we can use for this. And the parallel postulate says if there is a line and a point not on the line, then there is exactly one line through the point parallel to the given line. This is a big postulate for what we need in geometry. It's saying if I have a line L and I have a point P, there is only one line that goes through P that would be parallel to L. Not 2, not 3, not 0. One line that will go through that point that is parallel to it. So we always have exactly one that will go through that point. This lets us define parallel. And now we're going to go through problems, and we're going to see that's a major theme throughout the chapter. Perpendicular postulate carries with the same idea. If there's a line and a point not on the line, so if you have line L and then point P, then there's exactly one line through the point perpendicular to the given line. So if we draw that line down so it's perpendicular, there exists one. We can't draw another line that gives us a right angle. There is only one. Now, let's start looking at a certain type of diagram we're definitely going to see in this section and the following two. After this, this is where we have two lines and a transversal. So we say a transversal is a line that intersects two or more lines. So I have my transversal T here, and I have these two lines. For the sake of this section, we're just going to assume they're two lines. Later on, in section 2 and 3, we deal with these lines being parallel. We're not there yet. Today, it's just looking at location. Well, for this section, it's just looking at location for the different types of angles. So you're going to see two lines and a transversal that intersects those two lines at two different points. So our first one is corresponding angles, and corresponding angles occupy the same positions. So we'll start with one at a time. Say that angle 1 and angle 5 are corresponding. If I look, they're both in the top left of the intersection. Here's 5, there's 1, same location, same position. 2 and 6, top right, same location. 3 and 7, bottom left, same location. 4 and 8, bottom right, same location. So those are corresponding angles. Same location. Their location corresponds to one another at the separate intersection. The next one is alternate interior angles. So before we even look at what they are, we're going to think of alternate being on opposite sides of the transversal. And we're going to think of as interior between the lines. Or we could say inside. So, when I see alternate interior, I'm looking at opposite sides of the transversal between the lines. So that would be 3 and 6, 4 and 5. So 3 and 6, 4 and 5, we would say are alternate interior. Now we go alternate exterior. Well, there's that alternate word again. So it still means opposite sides of the transversal, but now when we say exterior, we want to say outside. So outside the lines, we're going to have 1 and 8, 2 and 7. They're on opposite sides on the outside. For our last one, consecutive interior angles, we have a new term, consecutive. Now interior we've already seen. We know that's between the lines, but consecutive, we want to think of next to, or nearby, or if we think of consecutive integers, the ones next to each other. Now, it's not opposite. And that's really where it's going to help. It's not on opposite sides of the transversal. So, consecutive interior, in between the lines on the same side. 4 and 6, 3 and 5. So those would be our consecutive interior. These are the key terms. They will kind of determine where the location is, corresponding to the other one, and that is same location. So let's take those and start naming pairs. So defined them, now let's name what we have. So name all pairs of corresponding angles. Corresponding, we think same location. Now, before I start naming these off, this may be a good time. You pause it, you go through, try all of these, and then we'll see if we match as we go through them. But name all pairs of corresponding. I have angle 1 and angle 5, both on the top left. Angle 2 and angle 6, both top right. Angle 3 and angle 7, both bottom right. Angle 4 and angle 8, both bottom left. Pairs of alternate exterior, outside the lines, opposite sides. 1 and 7, 2 and 8. Okay, vertical angles. Well, wait, that's not something we've talked about, but we still have pairs of those angles. Those are on opposite sides of the vertex. So 1 and 3, 2 and 4. as well as 5 and 7, and 6 and 8. Consecutive interior. Consecutive means next to or the same side. Interior means in between the lines. So that would be 4 and 5, as well as 3 and 6. Linear pairs, next to each other, adjacent, they're supplementary. We actually have quite a few of these. I have 1 and 2, then also 1 and 4, then we could say 2 and 3, 3 and 4, so any of them next to each other all the way around, and then it works the same way on the bottom. We'd go 5 and 6, 6 and 7, 7 and 8, and 5 and 8. Okay, last, pairs of alternate interior. Opposite sides of the transversal, in between the lines. That'll be angle 6, and angle 4, then angle 3, and angle 5. So there's all the pairs we could identify in the diagram. Now, here's a new diagram, new angles. We're being given pairs, and we have to identify which one they are. So 9 and 13. Well, let's see. They look like they're in the same location, different intersections, so those are going to be corresponding. 9 and 14. Okay, opposite sides of the transversal. One's on top of the transversal, one's on the bottom. Outside the two lines, so that's going to be alternate exterior. 10 and 12. Okay, same side of the transversal, in between the lines, so that's going to be consecutive interior. 9 and 11. Well, they're on the same intersection. They're adjacent to each other. Those are going to be a linear pair. 11 and 12. In between the lines, opposite sides, opposite alternate, in between interior, alternate interior. 8 and 15, outside the lines, opposite sides, alternate exterior. 12 and 15, they're at the same intersection, but they're on opposite sides of the intersection. Those are going to be vertical angles. Then 10 and 14, same side of the transversal, but one's inside, one's outside, but they're also in the same location. That makes them corresponding.